deep space exploration depends heavily on advanced propulsion technologies, the key to sending spacecraft far beyond our solar system. Among these, ion propulsion stands out. It uses electric fields to accelerate ions, generating thrust with remarkable efficiency. This system consumes far less fuel than traditional chemical rockets, making it ideal for long-duration missions. Another promising method is the solar sail, which captures the momentum of sunlight, specifically photons, to gradually accelerate spacecraft. Over time, this technology could enable travel to the outer planets and even beyond without using any onboard fuel. Nuclear thermal propulsion is also gaining attention. This system uses a nuclear reactor to heat a propellant like hydrogen, producing thrust. It offers a much higher specific impulse than chemical propulsion, potentially cutting travel time to Mars and other distant destinations. Looking further into the future, scientists are exploring fusion propulsion, which would harness the immense energy from nuclear fusion reactions, the same process that powers the sun. Though still theoretical, fusion propulsion could one day enable fast journeys across the solar system and even to nearby stars. There's also research into antimatter propulsion. When antimatter collides with regular matter, it releases enormous energy. This could, in theory, produce extremely high speeds. However, creating and storing antimatter remains a major challenge. Another innovative idea is beamed energy propulsion. Instead of carrying heavy fuel loads, spacecraft could receive power wirelessly from Earth or orbiting satellites using lasers or microwaves. This could allow lighter spacecraft to travel deep into space more efficiently. In the present day, electric propulsion systems like Hall effect thrusters are already in use on satellites and space probes. They've proven to be reliable and efficient, offering a solid foundation for longer missions. A related concept being explored is in situ resource utilization, especially using asteroid materials to create fuel in space. This would dramatically reduce the need to launch heavy fuel loads from Earth, making long missions more feasible. Advancements in materials science are also vital. Lightweight, heat-resultant materials are essential for building spacecraft that can survive the extreme conditions of deep space while improving fuel efficiency. Meanwhile, the integration of artificial intelligence into navigation and propulsion systems is transforming spaceflight. AI enables spacecraft to operate more autonomously, especially important on long missions where human control is limited by distance and time delay. The bigger picture. Why invest so heavily in these propulsion technologies? First, there's the scientific drive to understand the origins of our solar system and the universe itself. Spacecraft must reach distant planets, asteroids, and comets to gather vital data on their structure and formation. Reaching places like Jupiter, Saturn, or even farther, requires systems that can sustain years-long journeys. Another major goal is the search for extraterrestrial life. Moons like Europa and Enceladus may harbor subsurface oceans. Missions to these worlds require efficient propulsion systems that can make the trip faster and possibly return samples to Earth. Deep space missions also help us probe fundamental physics, studying gravity, cosmic rays, and dark matter in regions beyond current reach. For this, advanced systems like nuclear propulsion or even futuristic ideas like warp drives may one day be necessary. Resource mining on asteroids is another motivation. These bodies may hold valuable materials for space infrastructure or even Earth-based needs. To exploit them, we need efficient propulsion to minimize time and energy spent on travel. Lastly, the dream of sending humans to Mars and beyond is becoming more real. Human missions require not just faster travel, but also safe, stable propulsion systems that support life on board for extended periods. That includes shielding from radiation, reliable life support, and systems that reduce the psychological strain of isolation. In short, the evolution of propulsion, especially beyond chemical rockets, is not just about faster spaceflight. It's about enabling the future of exploration, science, discovery, and perhaps even survival. As we strive to overcome the immense challenges posed by the vast distances and harsh environments of outer space, chemical rockets have long been the backbone of space exploration. These rockets operate by rapidly combusting propellants to produce thrust, powering missions such as the Apollo program to the Moon and the Space Shuttle program that enabled regular access to low Earth orbit. However, as space exploration goals expanded to include destinations like Mars, the outer planets, and even interstellar space, the limitations of chemical propulsion became increasingly clear. This led to the need for new technologies and innovations. One significant advancement in chemical rockets is the development of more efficient engine designs, including staged combustion cycles. These cycles maximize energy extraction from propellants and allow higher performance. A notable example is NASA's Space Launch System, SLS, designed to support deep space missions. Additionally, the introduction of new propellant combinations, such as liquid oxygen and methane, has improved efficiency and reduced environmental impact. These new fuels make rockets more powerful and cleaner. Hybrid rocket systems, combining solid and liquid propellants, have also emerged. They offer better thrust control and can be throttled or shut down easily, important features for missions requiring precise maneuvering. Successful tests of these hybrid systems show great promise for future deep space exploration. Beyond chemical rockets, alternative propulsion technologies have gained attention. For instance, ion propulsion uses electric fields to accelerate ions, providing a gentle but continuous thrust that builds over time. This makes ion engines ideal for long-duration missions where minimizing fuel consumption is critical. NASA's Dawn spacecraft, which explored the asteroid belt, successfully used ion propulsion to travel vast distances using only a fraction of the fuel traditional rockets require. Solar sails represent another innovative approach. These spacecraft deploy large reflective sails that harness the pressure of sunlight, propelling them without any onboard fuel. This technology offers a novel method for traveling across the solar system, especially for extended missions. Despite their successes, chemical propulsion systems face several challenges for deep space exploration. A primary limitation is the large amount of propellant needed for long missions. Since rockets rely on burning fuel and oxidizer, any additional maneuvers require carrying extra fuel, increasing spacecraft weight. This added mass reduces payload capacity for scientific instruments and life support systems, limiting mission scope. Furthermore, chemical propulsion's efficiency, measured as specific impulse or thrust per unit of fuel, is relatively low compared to alternatives like nuclear thermal or electric propulsion. Although chemical rockets provide powerful thrust, they consume fuel quickly, which can extend travel times and complicate mission planning. Prolonged exposure to space's harsh environment also risks degrading spacecraft instruments. Operational constraints exist as well. In space's vacuum, combustion can be less predictable, making fine control of thrust during critical mission phases, like orbital insertions or trajectory corrections, challenging. Thermal management is another concern. Chemical rockets generate intense heat, which can threaten spacecraft structure if not properly dissipated. A complex task without an atmosphere. Sustainability also matters. The reliance on finite Earth-based propellant sources may limit long-term exploration, especially for missions to distant targets requiring large fuel reserves. In contrast, electric propulsion systems offer a different approach. Instead of combustion, they use electrical power to accelerate ions or plasma, producing thrust more efficiently. Electric engines have a higher specific impulse, allowing spacecraft to operate for longer periods and gradually build speed. Though their thrust is lower than chemical rockets, the extended operation results in high final velocities, perfect for deep space travel. Electric propulsion also reduces the fuel mass spacecraft must carry, potentially lowering launch costs. NASA's Dawn mission is a prime example, successfully demonstrating ion propulsion's benefits for exploring the asteroid belt. While chemical propulsion remains essential for initial launches and quick maneuvers, electric propulsion is becoming increasingly important for long-duration missions, where fuel efficiency and sustained thrust are key. The key difference between chemical and electric propulsion lies in how they generate thrust. Chemical propulsion is ideal for immediate, high-thrust needs, such as launch and quick maneuvers, whereas electric propulsion excels in efficiency over extended periods, making it perfect for missions requiring gradual acceleration and high fuel economy. As technology advances, innovative combinations of propulsion systems are emerging. Electric propulsion systems have become increasingly popular due to their efficiency and ability to provide continuous thrust over long durations. Ion thrusters ionize a propellant, typically xenon gas, and use electric fields to accelerate these ions, producing thrust. This method achieves a high specific impulse, meaning it uses less fuel over long periods. Ideal for deep space missions. NASA's Dawn spacecraft, which explored the asteroid belt, successfully utilized ion propulsion to travel vast distances, with remarkable fuel efficiency. Hall-effect thrusters. Similar to ion thrusters, Hall-effect thrusters use a magnetic field to trap electrons that ionize the propellant gas. Known for fuel efficiency, these thrusters have powered missions like the European Space Agency's Bepi-Colombo mission to Mercury. They provide significant thrust while consuming less power, enabling longer missions without frequent refueling. Plasma propulsion systems. These systems also use electric fields to accelerate charged particles, but can operate with various propellants. Still under development, plasma propulsion promises very high speeds that could revolutionize interstellar travel beyond our solar system. Electrospray thrusters. Utilizing electric fields to accelerate tiny liquid propellant droplets, these thrusters are well suited for small satellites or CubeSats. They provide precise control for attitude adjustments and station-keeping maneuvers, essential for maintaining satellite orientation. Radio frequency ion thrusters. Still experimental, these thrusters use radio waves to ionize propellant gas, potentially combining benefits of existing technologies for even more efficient propulsion. They provide continuous low-thrust acceleration over extended periods, unlike chemical rockets that deliver short, high-thrust bursts. This allows spacecraft to gradually build high velocities, opening possibilities for missions to distant worlds. They use xenon gas, which is abundant and easy to store, supporting ambitious missions to Mars, outer planets, and their moons, some of which may harbor life. Precise maneuvering capabilities make ion propulsion invaluable for delicate operations like orbit insertions around distant celestial bodies, where small trajectory errors can jeopardize a mission. Ongoing developments include more powerful ion engines and Hall-effect thrusters capable of increased thrust, potentially enabling larger payloads or human deep space missions. These advances will help unlock new scientific discoveries and future planetary colonization. Hall-effect thrusters operate by ionizing xenon propellant within a chamber. Electric fields accelerate the positively charged ions, while magnetic fields confine electrons, creating efficient thrust. Their specific impulse can exceed 3,000 seconds, compared to about 450 seconds for chemical rockets. This results in longer operational lifetimes and less propellant consumption. These thrusters can run continuously for hours, days, or months, allowing precise velocity adjustments, optimized trajectories, and better use of gravitational assists. They generate less waste heat, simplifying thermal management and enhancing system reliability. Because of these advantages, many modern spacecraft, including satellites and scientific missions, increasingly adopt Hall effect thrusters. Electric propulsion systems are often powered by solar panels, which generate electricity for ion thrusters. Recent improvements in solar array efficiency enable spacecraft to operate farther from the sun, even in regions with weaker sunlight. NASA's solar electric propulsion systems leverage advanced solar panels and the latest ion thrusters, like the evolutionary xenon thruster, to provide higher thrust-to-weight ratios. This improves maneuverability and mission efficiency while reducing fuel mass and launch costs. Innovations in power management and thermal control protect these systems from extreme space conditions, ensuring optimal performance. Material science advancements have produced lighter, more durable components, further extending spacecraft lifetimes and propulsion efficiency. High-efficiency solar cells made from materials like gallium arsenide offer better performance than traditional silicon cells and are being tested for future space missions. Researchers are also exploring hybrid propulsion systems that combine solar electric propulsion with other technologies, such as nuclear thermal propulsion, to extend mission capabilities. Nuclear thermal propulsion uses a nuclear reactor to heat propellant, typically hydrogen, allowing spacecraft to travel farther and faster than with conventional chemical rockets. It has a higher specific impulse and can reduce travel time to destinations like Mars. While nuclear engines require traditional launch methods and raise safety concerns due to radioactive materials, modern designs focus on passive safety to minimize risks. Compared to chemical rockets, nuclear thermal propulsion produces less pollution and offers longer operational life, making it well-suited for deep space missions. Nuclear electric propulsion converts nuclear energy into electricity to power efficient ion or Hall effect thrusters. This system provides continuous thrust over long periods, reducing fuel needs and enabling longer missions with complex payloads. It can significantly shorten travel times to outer planets and supports onboard systems like life support. Advances in reactor design improve safety and efficiency, making NEP a promising technology for future space exploration. EO, in situ resource utilization, ISRU, involves using materials found on the Moon, Mars, or elsewhere to produce fuel and supplies. Extracting water from soil to create hydrogen and oxygen propellants allows spacecraft to refuel on site, reducing reliance on Earth. ESRU enables hybrid propulsion systems that combine traditional and advanced methods, making missions more sustainable and efficient. It also opens possibilities for using exotic fuels like helium-3 for future fusion propulsion. Overall, ISRU helps lower launch costs and supports the long-term goal of establishing human presence beyond Earth. 3D printing, or additive manufacturing, is transforming aerospace, especially in building propulsion systems for deep space missions. It allows engineers to create complex, lightweight parts that improve fuel efficiency and performance. NASA uses this technology to make rocket engine components faster and cheaper, with the ability to produce parts on demand. Crucial for missions far from Earth. Advanced materials like high-strength alloys, composites, and ceramics are combined with 3D printing to make parts that withstand the extreme heat and pressure of space travel. These materials help engines run more efficiently and last longer. Additive manufacturing also simplifies supply chains by producing many parts in-house, speeding up production and reducing delays. It complements in situ resource utilization, ISRU, where local materials on the Moon or Mars are used to create parts, cutting down the need to carry everything from Earth. New propulsion technologies are also evolving. Nuclear thermal propulsion uses a nuclear reactor to heat hydrogen fuel, potentially cutting travel time to Mars in half. Nuclear electric propulsion uses nuclear power to drive ion thrusters, providing continuous, efficient thrust for long missions. Solar sails use sunlight pressure for fuel-free propulsion, while plasma engines offer high efficiency through ionized gases. ISRU techniques extract fuels like oxygen or methane from Mars' environment to refuel spacecraft, making longer missions more sustainable. Future propulsion may even include antimatter engines, which produce enormous energy by annihilating matter and antimatter, potentially enabling interstellar travel within human lifetimes. Together, these advances in manufacturing, materials, and propulsion promise to revolutionize space exploration, making missions faster, more efficient, and more ambitious. Antimatter propulsion could offer incredible efficiency, allowing spacecraft to carry less fuel and more scientific equipment or crew. This would enable faster missions to distant places like the outer planets and the Kuiper Belt, unlocking new opportunities for scientific discovery. However, antimatter is extremely costly and difficult to produce. Only tiny amounts are made in particle accelerators, costing trillions per gram. Storing antimatter safely is also a big challenge, because it must be kept away from normal matter, usually by using magnetic or electric fields, which aren't yet practical for large-scale use. Handling antimatter's immense energy release requires advanced systems, and current designs are mostly theoretical. Safety concerns are serious, since even a small leak could cause catastrophic explosions. Radiation from antimatter reactions also poses risks to astronauts and equipment. Political and ethical issues around antimatter use, especially in weapons, add further complications. On the other hand, plasma propulsion uses ionized gas, accelerated by electric fields, to produce efficient, continuous thrust. This technology offers great fuel savings and is ideal for long missions, allowing spacecraft to gradually increase speed. It's promising for missions to Mars, the outer planets, and long-term space operations. Plasma propulsion might also be combined with solar sails to extend mission range. Laser propulsion uses powerful ground or space-based lasers to push spacecraft with special reflective sails. This method could achieve very high speeds without carrying fuel on board, making spacecraft lighter and able to carry more instruments. Projects like Breakthrough Starshot aim to use this for tiny probes to reach nearby stars. Safety, precision aiming, and adapting to changing flight paths are key technical challenges. Solar sails harness sunlight's pressure to propel spacecraft. They are well suited for deep space missions because they don't need fuel, relying instead on constant light pressure for gradual acceleration. This makes them ideal for very long journeys where carrying fuel isn't practical. Solar sails use sunlight to push spacecraft by reflecting light off large, thin, and lightweight sails made from materials like mylar or kapton. Unlike traditional rockets that burn fuel, solar sails can keep accelerating as long as they catch sunlight, making them great for long missions. They have been tested successfully, such as in the Planetary Society's Light Sail project. However, solar sails have some challenges. Their acceleration is slow, they become less effective farther from the sun, and they are vulnerable to damage from space debris. Steering them also requires precise control. Beamed energy propulsion works by sending energy through lasers or microwaves from Earth or orbit to a spacecraft, which uses that energy to create thrust. This allows spacecraft to be lighter, since they don't need to carry fuel, enabling faster travel and shorter trips to places like Mars. The main difficulties are keeping the energy beam accurately focused on the moving spacecraft and ensuring safety to prevent harm to other space objects, or Earth. Scientists are also exploring breakthrough propulsion technologies that go beyond traditional rockets. Concepts like the theoretical warp drive could allow faster-than-light travel, making trips to other stars possible within a human lifetime. Advances in ion thrusters, plasma engines, and solar sails may also improve efficiency and enable longer missions. Combining these new propulsion methods with artificial intelligence could allow spacecraft to navigate and adapt in real time. These innovations could open the door to establishing human bases on the Moon, Mars, and beyond, expanding humanity's reach into space. Magnetic propulsion is an exciting concept that uses magnetic fields to generate thrust, making it promising for deep space exploration. It works by interacting magnetic fields with charged particles to push a spacecraft forward. One method, called electromagnetic sails, uses long conductive wires to catch the solar wind, a stream of charged particles from the sun, producing continuous thrust without fuel. This could enable long missions to distant planets or even beyond our solar system. Another advanced magnetic method is the magnetoplasma dynamic, MPD thruster, which accelerates ionized gases using magnetic fields. MPD thrusters are more efficient than chemical rockets and suitable for long missions, especially to outer planets, where travel distances are vast. These systems can be powered by solar panels or nuclear reactors, providing sustained thrust for high-speed space travel. Magnetic fields can also be used for precise spacecraft maneuvering by adjusting their strength and direction, helping spacecraft change course without fuel. In addition to magnetic propulsion, other advanced technologies are being developed for deep space travel. Ion propulsion uses electric fields to accelerate ions, offering high efficiency and long-duration thrust as seen in NASA's Dawn mission, exploring the asteroid belt. Solar sails use sunlight pressure to slowly accelerate spacecraft over time, demonstrated by the Planetary Society's light sail missions. Nuclear thermal propulsion heats propellant with a nuclear reactor, providing more powerful thrust and reducing travel times to destinations like Mars. Electromagnetic propulsion systems like the Variable Specific Impulse Magnetoplasma Rocket, VASIMR, offer flexible thrust levels, adjusting speed and efficiency depending on mission needs. Antimatter propulsion, still theoretical, could deliver enormous energy from small fuel amounts, potentially revolutionizing space travel by allowing rapid trips to distant stars. Beamed energy propulsion uses lasers, or microwaves, from Earth or orbit to push spacecraft, enabling lighter designs that don't carry fuel. The choice of propulsion impacts spacecraft's speed, maneuverability, and fuel needs. Traditional chemical rockets are powerful for launching from Earth, but inefficient for long missions. Ion engines and solar sails provide efficient long-term thrust, but with lower acceleration. Mission planning carefully considers propulsion type, launch timing, and trajectory to optimize travel. Safety and reliability are critical for advanced propulsion. Ion drives have low thrust, requiring longer travel times, increasing exposure to space radiation, which is a major risk for astronauts. Nuclear propulsion systems need strong radiation shielding and safety protocols to prevent leaks. Because many new propulsion technologies are still experimental, designing systems with backups and fail-safes is vital to ensure mission success. Training astronauts to operate and troubleshoot these systems is also essential, given the challenges of deep space travel. Overall, advanced propulsion technologies offer exciting possibilities to explore the solar system and beyond. Their development will shape the future of space exploration, making longer, faster, and safer missions possible. Advanced propulsion systems are transforming space travel by drastically cutting journey times to planets and moons in our solar system. Traditional chemical rockets, while reliable, are limited in speed and efficiency. New technologies like ion propulsion use electric fields to accelerate ions, allowing continuous thrust over long periods and greatly improving fuel efficiency. Nuclear thermal propulsion heats propellant through nuclear reactions, potentially doubling spacecraft speeds and enabling trips to Mars in weeks rather than months. Solar sails, still experimental, use sunlight pressure to propel spacecraft with almost no fuel, offering the potential for fast, long-distance missions. These technologies not only promise quicker and more feasible missions, but also bring important environmental considerations. While chemical rockets emit pollutants, ion drives rely on electricity that must be sourced sustainably to truly reduce impact. Solar power is cleaner, but involves environmental costs in manufacturing. Additionally, protecting other celestial bodies from Earth contamination and managing space debris are vital concerns that propulsion systems must address. Propulsion choices greatly influence spacecraft design, affecting weight, fuel needs, and mission capabilities. Electric propulsion enables lighter, more efficient crafts, but requires longer travel times due to lower thrust. Careful planning ensures spacecraft remain balanced as fuel is consumed. International collaboration accelerates progress by combining expertise and sharing costs, making advanced propulsion development more achievable. Overall, these advances are key to making routine missions to Mars and beyond possible, opening a new era in space exploration. International collaboration in space exploration leads to bigger and more ambitious projects like the Artemis program, which aims to return humans to the Moon and eventually send astronauts to Mars. Multiple countries contribute resources, expertise, and technology, boosting mission success and pushing propulsion technology forward. Collaboration not only shares costs, but also sparks innovation and competition, encouraging scientists and engineers to develop new ideas like nuclear thermal propulsion, which could cut travel time to distant planets. Working together helps establish common safety and regulatory standards, essential for complex missions involving many nations. It also promotes educational exchange and workforce development, training future engineers and scientists worldwide. Partnerships between government agencies and private companies accelerate propulsion advancements. For example, NASA's collaboration with SpaceX and Blue Origin has led to major rocket innovations. Private companies bring agility and fresh ideas, speeding up testing and development. SpaceX's Raptor engine, using methane and liquid oxygen, points to more sustainable fuels for Mars missions, improving efficiency and reducing fuel transport challenges. Shared knowledge between public and private sectors fosters breakthroughs. Programs like NASA's Innovative Advanced Concepts support small businesses developing novel propulsion technologies. Competition among private firms drives progress, with companies aiming to create faster, safer, and more efficient engines. Loki's gonna make useless engine. The integration of AI and machine learning into propulsion systems is another promising area. AI can optimize propulsion performance, analyze large data sets, improve mission planning, and predict maintenance needs, enhancing reliability and safety. Economic factors also shape propulsion technology. Government funding, private investment, and the potential for commercial space ventures drive innovation. As the space industry grows, through satellite launches, tourism, and mining, demand for advanced propulsion rises. International competition pushes countries to invest heavily to maintain leadership in space capabilities. Material costs and the availability of skilled engineers affect project budgets and success. Overall, the mix of funding, collaboration, competition, and technology development influences the future of propulsion. Advanced propulsion methods like nuclear thermal, ion propulsion, and solar sails promise to revolutionize space travel. reducing trip times and enabling human colonization of other worlds. Looking ahead, developments in electric and hybrid propulsion could also transform aviation and logistics, reducing emissions and fuel use. By 2040, propulsion systems are expected to be more efficient, sustainable, and powerful. Technologies like plasma propulsion, space tethers, and AI-optimized engines will expand our ability to explore the cosmos more safely and affordably. These advancements will open new frontiers for humanity beyond Earth. Algorithms powered by AI can dynamically adjust thrust levels and fuel consumption in spacecraft based on changing conditions, such as shifts in weight due to fuel usage or unexpected obstacles. This adaptability enhances fuel efficiency, which is crucial for long-duration missions because conserving fuel extends both the range and lifespan of the spacecraft. Additionally, AI's ability to process large amounts of data quickly allows it to simulate various scenarios and determine the most efficient propulsion strategy for a specific mission profile, something that would take humans significantly longer to compute. AI also plays a critical role in the design of propulsion systems themselves. Using generative design techniques, AI algorithms explore countless design possibilities and analyze them against performance metrics. This method can lead to innovative propulsion solutions that traditional engineering might not conceive. Furthermore, AI can simulate how these designs perform under various space conditions, ensuring that final built systems are optimized for both efficiency and reliability. During missions, AI enables autonomous decision-making. If a spacecraft encounters a propulsion issue, an AI system can analyze the problem, evaluate solutions, and implement corrective actions without waiting for ground control instructions. This capability is especially valuable in deep space missions, where communication delays make timely human intervention difficult. By empowering spacecraft with autonomous AI, mission reliability is greatly enhanced as the system can react in real time to unforeseen problems. AI facilitates the integration and management of advanced propulsion technologies, such as electric and ion propulsion systems, which require precise control to maximize effectiveness. Electric propulsion, like ion thrusters, uses electricity to accelerate ions and generate thrust, offering higher efficiency and allowing spacecraft to travel farther with less fuel. Similarly, solar sails harness sunlight momentum for propulsion, providing a fuel-free means to gradually accelerate spacecraft over time. A promising option for long-duration missions. Energy management is another key factor in mission sustainability. Renewable energy sources such as solar panels power spacecraft instruments, reducing reliance on finite fuel. Radioisotope thermoelectric generators, RTGs, provide steady energy for missions to distant regions where sunlight is weak. Coupled with advanced energy storage, these technologies ensure continuous operation without rapid depletion of energy supplies. In-situation resource utilization, ISRU, is a growing focus for sustainability. Using local resources on celestial bodies, such as extracting water from lunar ice or Martian soil, could drastically reduce the need to launch supplies from Earth. This lowers mission costs and environmental impact while aligning with sustainability principles. Designing spacecraft with recyclable materials and considering their full life cycle further enhances environmental responsibility. While advanced propulsion technologies offer exciting possibilities, they also raise important ethical concerns. One major issue is the potential impact on extraterrestrial environments. Introducing Earth-based microorganisms or human presence could disrupt fragile ecosystems on other planets or moons, possibly causing irreversible changes. Scientists and ethicists argue for responsible exploration that protects these unknown worlds, especially missions to Mars or icy moons like Europa and Enceladus, where signs of past or present life may exist. Resource allocation presents another ethical dilemma. Developing propulsion technologies often requires substantial investment, which raises questions about whether these funds could be better spent addressing urgent Earth-bound challenges, such as poverty, climate change, and healthcare. Equity and access issues also emerge, as the benefits of space exploration may disproportionately favor technologically advanced nations, potentially widening global disparities. The militarization of space is a further concern. Advanced propulsion could enable rapid deployment of satellites or weapons, risking escalation and conflict in what has traditionally been a peaceful domain of international cooperation. Ethical responsibility demands efforts to keep space a collaborative arena rather than a contested one. Finally, the prospect of human expansion into space prompts questions about the rights of future generations and the legacy we leave behind. Should we establish guiding principles to prevent exploitation of extraterrestrial resources, similar to Earth's environmental regulations? The potential mining of asteroids or other celestial bodies calls for careful governance to ensure sustainability beyond our planet. Funding for propulsion technologies is vibrant, with governments and private sectors investing heavily. NASA and other agencies allocate significant budgets toward developing advanced systems such as electric and nuclear thermal propulsion to reduce travel times and increase payload capacity for deep space missions. Private companies like SpaceX and Blue Origin invest in reusable rockets and innovative propulsion methods that lower costs and improve efficiency. Public partnerships are becoming more common, combining government resources with private expertise. Small satellite launches have created niche markets for propulsion technologies, tailored to smaller payloads, attracting investment from both private investors and government grants. National security agencies, like the U.S. Department of Defense, also fund propulsion research for strategic advantages. Internationally, countries such as China and India are increasing investments to develop indigenous propulsion technologies supporting ambitious space programs. This global competition accelerates research funding and technological progress, pushing the boundaries of what is possible for interplanetary travel and advanced satellite operations. Advances in propulsion technology open new horizons for humanity's quest to discover extraterrestrial life. Faster, more efficient spacecraft mean shorter travel times to distant planets and moons, enabling more frequent and in-depth exploration missions. For example, ion propulsion and solar sails allow missions to potentially habitable exoplanets and outer solar system bodies with less fuel and greater speed. More speculative technologies, such as nuclear thermal or antimatter propulsion, could dramatically shorten travel times to other star systems, crucial when considering vast interstellar distances. Traveling at significant fractions of light speed might make it feasible to reach nearby star systems like Alpha Centauri within decades, rather than millennia. Improved propulsion also supports larger, more capable spacecraft, equipped with advanced instruments to analyze exoplanet atmospheres, search for biosignatures, and even return samples to Earth for study. Missions to icy moons with subsurface oceans, such as Europa and Enceladus, become more achievable, potentially leading to groundbreaking discoveries about life beyond Earth. Missions to groundbreaking discoveries about life beyond Earth.